Alright guys, today we'll be starting a new tutorial series on deep learning papers, machine learning papers. And so today we shall be looking at this paper, Playing Atari with Deep Reinforcement Learning. Essentially, to be able to understand a deep learning papers, we require some background knowledge. So it might be very difficult for me in less than 7 minutes to cover all the background knowledge. But I'll try as much as possible to give my understanding of these papers. Hopefully there are other materials out there that you can source to give you a better background knowledge or details of some of these things. So the Atari is a game, and the deep is coming from the further concept of the deep neural networks. And the reinforcement learning, it's another mechanism whereby an agent, and when I mean an agent, it's synonymous to a robot or to a human being, something in that direction, who is able to learn by experience and reward. So that's essentially what's happening. So in this paper, the work is combining the reinforcement learning techniques with deep neural network to be able to develop an agent that is, in this case, is a game agent that is able to perform very well in playing games and even defeat the best human players. So there are some important terminologies and very many important concepts that lays the background to this work. One of them is the control policies. So policy is essentially talking about the probability. So when you say policy, you're talking about the probability of taking an action given a particular state. And of course, I guess you're familiar with convolutional neural network, which is a layer of neurons that can approximate arbitrary function. So we refer to neural network as a function approximator, and the convolution here is as a result of the fact that in this work we feed in the pixels, the images of the games into the network. So that's why we're using the convolution, which is proven to work very well in processing image data. So the way this work is done is you get at sample, as you can see, this is the different states that the game could be. Each of these are different states that the game could be. So these are the images, and a sequence of images forms like a video. So a game is continuous, it's not static. So you keep having changes from one time step to another. So that's an important concept, and the queue learning is also an important function. Now, there's what you call the value function. And you have the queue, queue, the state value function, and the action value function. So essentially, what the queue learning is trying to do is this: the queue learning is a function that will output a value that shows how good is taking an action in a particular state. I repeat myself, the queue learning is actually a function that output a value that tells us a how good is taking an action from a particular state. So let's go into into the paper and see some other concept as you go down. So this is the screenshot, like I mentioned, from some of the different kind of games. But in a particular game, you can have different time step, different images from a particular uh, game, because each of these items, each of these players can be in different position at different times. So let's look at the background of the work. So some important concepts here. You have a set called A, that's capital A, which is a set of actions that can be taken. So at each time step, the agent selects an action. So what is a time step? A time step typically it's abstract, but you can consider a time step using an example. Say for instance that the 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 agent observes the state of the game and takes an action and gets a new state as well as a reward. That's a time step. When it takes another action, that's another time step. When it takes another action and you observe the state of the environment, takes another action and the state changes as a result of this action, and the agent receive another reward, that's another time step. So that's a time step. So at time step small t, the there are different action. At time step small t, that is the action uh, the agent can take, represented by 80. Now, the total number of actions that the agent can take is k. So that's represent the possible number of actions. For instance, in some games, in like tie games, your agent can just move left, right, top, down. So that's k. So in that case, k is 4. In some games, the number of actions is infinite. So now we also talk about this is xt, that is the agent is observing an image. So the xt is actually talking about the image from, like I explained before, and that image has a dimension d. Okay, so and a very important point again is the observations. Now we therefore consider sequences of action and observation. Now an observation, which is represented by s of t, that's a sequence. So the agent observes the environment, say for instance x1, which is an image. It takes an action at that state, which is a1. Then as a result of his action, the agent action, the environment transition to another state, which is x2. So the game changes to s2, and the agent takes another action a2, continuously like that. So this forms the s of t. Okay, so the agent learn the game strategies that depend upon this sequence. Now another important concept is the Markov decision process. Now, and this is a finite Markov decision process in which each sequence is a distinct state. Okay, so what's this saying? In computer science, there is a study of what we call formal language theory of finite automata. So that's essentially what they're saying. In a finite automata, it composes of a different state. You can have different states, and in each state, you can transition from one state to another by taking a particular action. So when you take an action from state 1, you can transit to state 2 based on a particular action, and you can also have a reward associated with that transition. So that's essentially what the Markov decision process is talking about. Okay, so in this case, each sequence is a distinct state. All right. So, and as a result, we can apply the standard reinforcement learning method to NDP simply by using the complete sequence SD at the stage representation at time t. Now, the goal of the agent is to maximize the reward obtained. And how does the agent maximize the future rewards? And that is brings us to another uh, concept, which is expected return. And this expected return is discounted. The reason why it is discounted by a factor known as gamma is because in this situation, this game is infinite. It's infinite, so it's continuous, and so we don't know exactly when the number of steps ends. So because the the agent keeps playing the game, and as a result we want to maximize the expected value by discounting the rewards over time. So like here now, you have the 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 expected return is discounted, so the RT is actually the reward, so you now discount that with gamma over time, and this discounted rate is structured in such a way that immediate actions, immediate reward is prioritized over later rewards in the game. Okay, so capital T is the times at which the game terminates. So we define an optimum action value. An optimum action value pair, which is represented as Q star, it's actually the combination of action taken in a particular state that maximizes the expected return. Okay, so so after seeing some sequence A and taking some action A, Q star is uh, the action, the optimal action value. It's given a state and an action, and is expected to return the optimum value, and that optimum value is represented with this equation. And what is this equation trying to tell us? Now, pi is, like I said, is the policy, the probability of taking an action given a state. And so we want to maximize the expected return. R is, and capital R is return. We want to maximize the expected return in a particular time step t, given that the state is equals to s, while s of t is a set of state, and the action at is equals to a, where a of t is a set of action, and given the policy. So essentially, in a neural network is helping us to be able to learn the policy, which is the mapping sequence to action over a distribution of action. Now, the optimal action value obeys what is known as the Bellman equation, and this is based on the following intuition. Let's say, for instance, that the optimum value is this of sequence this at the next time step when known from possible action A. Then the optimum strategy is to select that A prime. Okay, since that is it, which maximize the expected return R plus the discounted rate, as is given us in this place. This is the expected return, it gives us this maximum. Okay, yeah, so and so this is what we're having here. So if you sample S prime from the experience, this is the equation for the the optimum value. You sample S prime from the experience, that will be the reward plus the discounted rate of Q star S prime A given S and A. So essentially we're trying to get the maximum value from this function. So the basic idea is to estimate the action value function by using the Bellman equation in an iterative update, and that is what we're learning. So in our neural network, the Bellman equation serves as our ground truth, while the predictions from the neural network, which is QS of A, is we do a comparison between that and the Bellman equation to be able to estimate the loss and propagate back into the network to update it, and that's what is happening here. So we're trying to minimize the sequence of loss function. So this is the loss function. This is the result of our Bellman equation, y of I, and that is shown in this here. That is what is given here, and that is the same thing that we have here. That's the optimum. So that serves as our target. If we have taken anything on supervised learning, that's our ground truth. Now, this is what our neural networks gives us. This is the prediction of our neural network. This is parameterized by theta of I, which represent the weight. And so this is essentially a mean square error. So this is mean square error, and it is so because we are actually just doing a regression problem. We are predicting numbers. Okay, so we go through the normal neural network stuff, which is to do a back propagation. So when you differentiate the loss function, you have this, and that's essentially what is happening there. So on a final note, let's just look at the algorithm, since we have gotten some of these things here. And before we look at the algorithm, I'll just explain this, how the training data is generated. When you play the game, you store the experience as, for instance, the experience at the time t is the state at time t, and the action taken at time t, and the reward given back at time t, plus the new state after taking the action. So this 4 tuple makes of an experience. This experience is taken into a set which is known as the data D. So this form our data set for training. So like E1 will be S substitute 1, A1, R1, and that will be S2. And E2 will be S2, A2, R2, and S3, up to we get to the maximum number that we specified. Okay, this forms our data set. So when we now get into the algorithm, we will understand now better. Okay, so let's see the algorithm now. Yeah, this is the algorithm. Initially, we initialize the replay memory D to capacity N. This is just like getting our training set. For any neural network, you need your training set. In this case, the training set is our replay memory, which I've explained earlier. We initialize it to the particular N. That means we play the games and store all these things in N, and we store it in D up to a particular value N, like we saw in this list. This is up to E of N that we're seeing here. Now we initialize the action value function Q with random weight. This is essentially what you do for any neural network. In any neural network, for you to start, you have to initialize the action value function, the weight. You need to initialize that. Okay, so that's just initialization of the network. Now there's a concept of episode in some games. A game that has a finite number of steps can end a finite number of time steps can end up in make up an episode, and multiple we can have multiple episodes in a single game. So in this case we have m number of episodes in the game. So from number 1 to m, what do? We do all of this. We do all of this from the first episode to the last episode. So when we take each episode, the first episode, we need to get our training set. So we initialize our training set to a sequence. Now what is this sequence, which is a set x1? So the sequence is actually what we have explained earlier. So the sequence is the set of states and action which we look earlier here. Yeah, so this is our sequence. So this is our sequence. This, the image, the action, the image, the action. So these are sequence of action. So we initialize that in the algorithm. So our x1 is the initialized sequence s1 for that episode to this. And what do? We now preprocess the sequence into y1. What do you do in the processing? You take the image, you may need to crop the image, you may need to change the color image to grayscale. These are all some of the things that is done in this preprocessing of this. Now when you have that image which can be a mini batch, then you have a data set. So in that, what you now do is that you go from the first time step to the last time step. Remember I said in a particular episode you can have multiple time steps. So you, from the first time step, you, with a probability of epsilon, select a random action. How is this done? When your agent starts playing the game, the agent can either do what you call exploitation or exploration. Exploration simply means the agent is trying to learn information about its environment, while exploitation means that the agent is using the known information to be able to take appropriate action. So in order to have a trade-off, a balance of exploration and exploitation, we introduce an epsilon to give a probability, so that as the training begins, as the agent begins to learn, there are higher probability that the agent will do exploration. But as the training progresses, then the probability of exploration will reduce, while the probability of exploitation will not increase. So then we select a random action, takes an action out of a of t, sub t, like I said, is an element in the big A of the allowed capital A, like I said before. So in the allowed capital A. All right. Okay. So and this continues. So now this is if it does exploration. If it's not doing exploration, then it actually takes the greedy approach. The greedy approach is to do an exploitation by actually taking the action that maximizes its Q value, that is, that maximizes its returns, and that action is actually learned from based on the learning in the network parameterized by theta. It executes that action in the emulator, observes the reward, and the next image, which is the next forms the next time step. Then that now changes. The next image becomes the st plus 1 is set to st, at, and xt plus 1. That is the new sequence that we have. So this becomes the new sequences that we have. Then we reprocess again as we did here, file t plus 1 based on the new sequence. So this is like repeating the same thing here, but now in this case we now have a full sequence. In the first instance we just have the image, but now we have not taken an action which now forms part of our next sequence and the new state. So we preprocess that, then we store that transition in the data set. Then we sample random mini batches from that data set that we have here. Is this data set, which is from D. So this is our sample, which could be like 8, 16, 32 from here. So now we can do two things. If the game is a finite game, if it is terminal, then we set our y of j, which is actually our prediction, to r of j, which is the maximum expected reward. If it is a non-terminal game, then we set our y of j to this equation, which discount with a discounted rate, which is gamma, which discount the reward over time. This is for non-terminal sequence. Then we perform a gradient descent on the loss function, which is a mean square error. Then we do this iteratively until it converges. Then once we are done with this, until we get to the end of the time step for that particular game, okay, for that particular episode, I mean, once we are done with that, then we exit the loop, then we repeat the same thing for the next episode and continue like that until we reach the number of episode m that we have actually set. So m is a hyperparameter that we set. Capital T is also an hyperparameter. N is also an hyperparameter that we set. So there's a lot here. I hope I've been able to do some justice to some concept there. Let me know what your comments are. Thank you very much, and see you soon.